So good morning, everybody. I am Michele Sgamma. Today I'm presenting you a work that is actually a work of thesis of Francesco Fontana, which graduated just a couple of days ago, so it's not here. And yeah, it's a work that it's the first step, basically, in a wider work which follows the spread of electronics and printed circuit boards used into a lot of areas of industries like automotive, which is the closest to our works, but also aerospace, tractor industry, and more. And what we want to do is to deepen our knowledge about fatigue durability, or what is mechanical vibrations, what mechanical vibrations does to printed circuit boards and electronics, in order to let's say, act on the take, make, and waste life cycle of PCB, trying to avoid wasting PCBs, which are wasted even just one component is broken, or trying to test new materials in order to have more recycling and more circular life cycle. So talking of failures due to mechanical vibration, we can have four kinds of failures, but the two kind of failures we want to focus on are these two, which are solder failure and lead failure. And you can see from the picture below that they are both correlated to the acceleration or deformations due to the circuit board, so the PCB. For this reason, the aim of this work, that is the step zero, is to investigate how is this static and dynamic behavior of the PCB, and to try to model it with different kind of models and to assess which model is the most suitable to describe the dynamic behavior of the PCB. We've done it by comparing, of course, numerical results with experimental results. Here are the models we compared. Three of them, the one you see on your right, are ANSYS Sherlock based, which is a software recently bought from ANSYS. And the first model, the Sherlock model, is fully used on the Sherlock. So just you take the model from the ECAD and perform the simulation, while the other two, reinforcement and complete, also use ANSYS Mechanical and are of course more complete and more complex. The first two models, the ones on the left, are developed by Francesco, and they can be used with every FEM software, and simply they model different way the layers of the PCB. The first one calculates an equivalent thickness of the copper layers, while the second one include all materials in the calculation, and for every layer compute an equivalent density from the percentage of each material included in that layer. So as for the quasi-static tests, we made this kind of isostatic bending test, which is very different from a 3-point bending. It's more 4-point bending. And we choose this configuration because it's isostatic, and it helps a lot with simulation, with numerical computation of the model. So it makes it a lot easier. And coming to the results, here you can see, you can see even the video of the simulation is quite fast with no problem. Okay, that's a video, but trust me, the simulation was quite fast and easy. And the important part of these results is that you can see the Sherlock column, the Sherlock model doesn't give results for quasi-static testing because it doesn't allow to make them, just dynamic tests, dynamic simulation. As for the dynamic tests, we use, of course, a vibrating shaker, and we acquired the response, the vibrating response, with fiber optic laser in different points of the board of the PCB, in order to see better every mode from 0 to 1.5 kilohertz. You can see here the first three modes. And here are the results of these three modes, which show that for the first mode, which is the most important one, both on FRF that for participation, all the models are quite good in coming to good results comparing to the experimental one. But the first two models, which are the most simple, are even better than the last two, which are far more complex. For the second and third mode, the things are quite different. So the error is a bit larger, but still there is not so much difference between the simplest mode and the more complex one. Even the most complete, the most complex is the worst. This is important if we have a fast look also at the computational effort of each model. The last two models, especially the complete one, require a lot more of computational effort, a lot more of simulation time. And this request is not justified by the accuracy of the results. So for sure, the three models that we want to go farther with the study are the first three one. The first two that are easier, and we can say we can use, we know how they are made. We can use whichever software, so they have basically no problems in the use of them. The Sherlock, let's say the first Sherlock model, base Sherlock one, is precise and also fast. So it's for sure interesting to investigate further, to use with dynamical testing, while the most complex one would be, I think, abandoned for the future works. What will we do next? Of course, we are going to mount components on the PCB and try to investigate, firstly, the dynamic behavior, how this change with components mounted on, and then coming to the fatigue test to perform which are the failures we have seen before. So solder failure, lead failure, and trying to detect them by voltage drop or visual inspection, or even differences in natural frequencies and so on. So I tried to be as fast as possible. I concluded. I don't know, maybe there are no time, I don't know. Okay, so thank you.